In this design, I used discrete gate drivers to drive MOSFET half bridges. As you can see, I needed some reworks to get it running. Can you guess what went wrong? In this video, I will show how to design discrete gate drivers and what I had to do to get this one operational. To turn on MOSFETs, a gate source voltage is needed. In order to have low RDS(on) losses, a gate source voltage of 10 to 12 volts, as shown here in the datasheet, is preferred. The gate driver serves as an intermediate circuit between the controller or microcontroller and the power MOSFETs. On the market, there are plenty of gate driver ICs you can use. However, it's relatively simple to design your own. Now I'm very interested, what do you prefer? Do you prefer to design your own gate drivers or use the available gate driver ICs in the market? Please share in the comments. Now let's take a closer look at the low-side gate driver. The current is driven through a push-pull stage consisting of an NPN and PNP bipolar transistors. When a positive voltage is applied on the base, and therefore we have a positive current flowing through the base emitter, an amplified current flows through the collector emitter, turning the MOSFET on. The simulation is shown here. We have a positive voltage and the base current, and a higher collector current rushes into the gate source of our MOSFET. Likewise, when a low voltage is applied on the base of the PNP BGT, a higher collector current can flow, turning off our power MOSFET. A gate resistor limits the current that flows into the gate and is needed to limit noise and ringing. Now you might think that the push-pull stage connected directly to the microcontroller or controller is enough. However, we wanted to have an output voltage of around 10 volts or 12 volts, as stated earlier. And if we only connect a low voltage here, the output voltage of the push-pull stage is around 0.7 volts lower, because we have a voltage drop here from base to emitter of around 0.7 volts. Therefore, another stage is used to have a higher output voltage, driving the power MOSFET. A simple way of doing this is to use a pull-up resistor and a signal MOSFET. When the MOSFET is driven and turned on, the push-pull input is low and the power MOSFET gate-to-source voltage is low and therefore turned off. When a low input voltage is applied on the signal MOSFET, a current can flow through the pull-up resistor and the NPN base and collector, turning the power MOSFET on. As you can see, the driving signal and turn on signal of the MOSFET is reversed. In order to turn on the high-side MOSFET, a higher voltage than the input voltage is required. This is needed because when the high-side MOSFET is turned on, we almost have the output voltage at the switch node, disregarding the RDS(on) losses, which are very low. And therefore we need a higher voltage to have a positive drain-to-source voltage, turning the high-side MOSFET on. To get a higher voltage than the input voltage, a Bootstrap circuit is used. This consists of a resistor and a diode and a Bootstrap capacitor. When the low-side MOSFET is turned on, the current from the drive voltage, which is here 10 volts, will charge the Bootstrap capacitor. Visible as well here, the low-side MOSFET is on and we charge the Bootstrap capacitor. And during the on period of the high-side MOSFET, the Bootstrap capacitor is discharged slightly. It is charged every cycle until a steady state is reached, and then only it's slightly recharged during the on period of the low-side MOSFET and discharged during the on period of the high-side MOSFET. The high-side gate driver is the same as the low-side gate driver, with the push-pull stage and the inverting stage with the signal MOSFET and the pull-up resistor. The only difference is the just discussed bootstrap circuit for getting a higher voltage than the input voltage. Here in the simulation we can see the signal coming from the PWM generator, which is inverted, and the drive signal drain to source for the high-side MOSFET and the output voltage here. In this simulation, the half bridge is controlled with the C++ block modulating an STM32 microcontroller PWM. Check out my last video to see how this is done. In my design here, I used the just discussed gate driver. However, the signal components always broke and the PCB got significantly hot. The reason for this was the selected component in KeyCut. I should have selected the component where the base is 1, the emitter 2 and the collector 3. However, I had the collector and emitter reversed. So when you select the component in KeyCut, I unfortunately selected base 1, collector 2, emitter 3. And I would have needed, according to the components I used in the end, the base 1, emitter 2 and collector 3. So should have used this component instead of that. To get it working anyways, I flipped the components, bent the legs down and rotated them to solder them still on the proper spot. Like this, I got the gate driver working and it works as intended. That's all about gate drivers so far. Thanks for watching.